Observe here, no doubts at all. But this time not later. Nothing clear about the doubt here. So if you have any clarification, any question, ask. Yeah. Yeah, that is a separate section. See, ocean transport heat from the tropics to the polar region, right? That's how they get the heat. And they also absorb CO2. So they got growth. So I think because the next I'm going to cover this question, so any other general specific topic will be covered by she will give those lectures, but I want you to basically have the overall picture about the economics. Yeah.
So you were saying that the temperature increases first, that have to observe that temperature increases first, and then the carbon dioxide increases. And subsequently the
The data of the last 20 years, last I think came out, you clearly see that first temperature increase in Antarctica, then the carbon dioxide came over the ocean, that increased temperature further, the feedback led. So the sequence is first temperature is dropped, then CO2 is covered over the ocean. That is one point. Yeah, but in the natural world, it's going to come to the ocean, not from the ocean. Now we are putting CO2, but so everything came, the CO2 came out of the ocean, went back to the ocean. So look at, for example, when the CO2 was only 180 degrees. Right down below, it all went into the land or ocean and out of the atmosphere. Then, sometimes it all came out. So the carbon dioxide is getting exchanged between ocean and atmosphere to long term. Yeah, so if there are no more questions now, let's continue our discussion. I said that the weakest point in the modeling that we do about the Earth climate system is clouds. That's because cloud comes in a variety of stages, and we are not able to model each one of them. So we use broad empirical formula, right? In this example of a complex cloud system, they all get the clouds here, the deep one, shallow one, and so on. So far, our models are not good enough to be able to show this one. Are not good enough to tackle each one of these clouds and their properties and so on. So we model the whole system, and that is unfortunately those which don't rain, which rain heavily and so on. And we, so these are not from first principles. These are put in empirically by various observations. And if you look at different models, different countries, the main difference is here. All the others are the same. You look at their way they handle the circulation or computation, all similar. The only difference primarily comes in the way they tackle clouds. Each group has a different model, and we see later that these differences unfortunately cause large differences in the prediction of global mean temperature. That is the main difficulty. Here is one example from one of these models. What they did was they ran this model in MCAR in World Colorado, ran the model without CO2 increase, and this is a blue line. This is called natural, that is, CO2 didn't go, but volcanic eruption occurred, solar, radiation, all that was put in, but human impact was not put, then temperature didn't change. It fluctuated, but didn't change. Then they added the increase in CO2, and also the effect of sulfate aerosols. Then you see this red line. And black line is observation. So there are three lines of black, red, and blue. Blue is without human impact, red is human impact, and this shading here shows the range of values. So there is not one number, because you have the model 100 different values. So there is a range of one single number here. But the key point to remember is that whatever range you are getting here with no human impact is much lower than what you are getting with human impact. And this is closer to operative. So to me, this is the true proof that human beings are influencing Earth's climate. Because if you believe these models, you cannot believe it. If you believe the model, then the model is saying that CO2 didn't increase, then the temperature would have fluctuated around the value of 15 degrees, which is removed in this graph, 150. While if you allow CO2 to increase, it goes more like 15.7. Okay. But I want to remind you that this red line does not follow the observation exactly. See, there are places where the model is not that good, like in the 60s or here. So these are to be expected because in the model, what we have put the CO2 increase that we know very well. But these changes in sun radiation and changes in aerosols and eruption of volcanoes, they are unfortunately not well known. Especially before 1960, before satellite came, our knowledge about the Earth is very, very poor. Okay? So you see that the disagreements are large here. You see that knowledge is there, that is to be expected. We don't know what happened in the 90s, what something happened, and we are not doing any correction. But in this period, we are doing quite well. In the period of satellite data, where we know precisely how the concentration of CO2 change and how sulfate change, we have predicted. But in the past, we are ignorant about what really controls the climate. But to me, this is the proof which clearly shows that in the last 50 years, all the increase that we saw is definitely related to human influence. And to make the point further, I want to show that the same graph in a different way. Here is observation is black and red is all parameters. Now, if you don't include sulfate aerosols, you get this result. If you fix aerosols in model at some value in the 20th century, then you can see temperature increase much more. So what this shows is that about 0.6 degree warming has been prevented because while we are burning fossil fuels, we not only emit CO2, we also emit aerosols. So some cancellation occurred purely by luck. We didn't know it, but happened. Now this is a very important issue because in the last 20-30 years, because of the concern about air pollution, all the major power plants are putting out special thing to remove the aerosols all over the city, especially in the developed world, Europe and America. They have put up on the stack special thing to remove the aerosol. So this particular advantage we had of pulling the aerosol will not be there in the future. Okay. So as India and China also decide that we want clean air, right now we have politicians and workers who don't understand how bad air pollution is to health. So many of them tell me pollution is the price you must pay for progress. Okay. And Indira Gandhi quite a ridiculous slogan saying that poverty is more serious than pollution, which is ridiculous. Okay. To me, both have to be controlled. It's not as though it is control poverty or pollution, both have to be controlled. And so this is the viewpoint in the developing world, where there are so many problems that we decided to one problem. But it's going to change, it's already changing, it's going to change. People are going to demand reduce air pollution, so this is going to go away, this aerosol effect. And when that happens, global warming will get more serious. Because sulfate was cooling the earth slightly, about by half actually, and that cooling effect is gone. So this is a major issue which is bothering many people, because the demand for controlling air pollution will come locally, not come in a global field. It's already in Delhi, you know, a big campaign in Delhi air pollution was partly controlled. So same thing will happen in our parts of India, it happens already in China. So this is going to happen due to local factor, not local. You have no control over it. No nation, nobody can control it. But CO2 is a different issue. CO2 is a global pollutant, not a local pollutant. Whether CO2 is released in London or New York or Beijing, it's being mangled in 1 week. Okay? So CO2 is a very unique pollutant compared to aerosol. Aerosols are local. If you release aerosol in Backlund, it may go maybe a few hundred kilometers. At the most, somewhere it will go mostly, and it will fall down within a week's time. and you'll hear about it from Satish when he gives a lecture. CO2 again, I want to remind you, keep reminding you, it's a unique pollutant that it is well within the atmosphere, and it reaches anywhere what you want, it will reach everywhere, and it has a lifetime of a couple hundred years at least. So that is what makes it such a deadly pollutant, because it is long-lived and it is local impact. The aerosol is short-lived and local impact.
Sir, in the previous plot, we showed the anomaly for 1890 to 1990.
Yeah.
It is used because of the pre-industrial age. First anomaly we are taking for 1890 to 1920 or something.
Now, normally, all these graphs, normally, if anomaly is this cannot given, the reference is usually this period. This period normally we choose to do anomaly because that's very good data. But here I don't know which period we use. Yeah. What do you think you're saying? What?
I am saying like it's written anomaly from 1890 to it's 1920, I think, 1990. So we are taking only pre-industrial period for taking anomaly. Or we are taking whole.
In this graph, the graph is drawn. I think we started with this other effect. So everything goes to 0 here. So I suspect in this graph, 0 reference is 1890 when it started. 1880.
So by 1920 or something.
Yeah, so I think all the anomalies is for 1890. That's what you're doing. Because everything else you see, all of them go 0 here. Right? So I suspect this is the departure temperature from this temperature, whatever it was.
But that time, the observation, like it's not sure how correct are they that time or number.
You don't know. See, that's a problem. See, you must remember that the biggest problem we have in the IISc report, they want to start pre-industrial. Because that is the time and there are no bosses here. But we have no data. Very little. As a matter of fact, in 1890, I'm sure there were observing maybe 100 stations in the world and few ships. We are right. That's a big problem that period. But if you want to start on positive fuels, you cannot start here, you have to start here.
Yes, right. Everything is showing significant increase.
Yeah. So one is this period, how to start with the product because you have not a very good quality data. And that's why I told you, my faith is only in this period. Because that data, everything is there. Before that, I don't know. A lot of, for example, during World War, a lot of perspective. There's no data during World War, half the stations are not working. So 1940, 1950 data is very important. So before 1960, everything is, so they can't get too serious. So only this period I focus on, the last period where we know that the data was of good quality. Because satellite data is your global picture. Before that, remember that we are trying to calculate global mean temperature based on 120 stations, which is not right. See, 70% of the Earth is ocean. We didn't have any data over ocean, please except ships. And ships going along only certain
specific rights.
Yeah. So it's very ridiculous. So a lot of people have criticized any analysis of global mean temperature before 1950. But I must tell you, people are doing a lot of serious work. The way people have looked at it is because you take, let's say, 1990 when you have a lot of good data. Okay? You calculate global mean temperature. Then in 1990, you pretend there are only 100 stations. Then you adopt some mathematical function, you calculate and calculate again, and the answer is more or less right. So the point is that if you assume that the spatial pattern temperature has not changed in the last 100 years, and whatever pattern was obtained last 50 years, you impose it on the past. So your 100 station data, remaining places you fit a function based on this, you can do that. People have done it. But you must remember a little error. That's why I'm not showing in this lecture, but I have one slide which shows global mean temperature from 3 different groups in the world. One is East Anglia, one is NASA, one is other group in US. You get 3 different values. Because they are also the same data, but they use different interpolation. You get different answers. So this is the penalty you have to pay. But the fact is that, the good news is that they differ by only 0.1 degree in each other. 0.1 degree is acceptable, can't do anything beyond 0.1. So that's why I'm confident with this value. I'm not confident here because here, this difference I can't really be sure. This I'm sure. This is 0.5, 0.6, 0.7 degrees. That I'm sure about. Anything around 0.1, we don't know. Okay, so one thing I must mention, all these models we have done over the last 100 days, they all predict these things. Increase in extreme temperature rainfall, less gold lines, and all of these have come true. Okay? Every one of the predictions the models made about what will happen due to CO2 increase have come true. So the models are not bad. Only reason why models are totally trusted is if you want what will happen rainfall in Bangalore 100 years from now, that is difficult. If you want local information about future, we are not sure. But if you want global information, that's very accurate. So suppose the models say the global temperature will go with 3 degrees. There may be an error about how can it is that way, but it will be true. But you want to know what will be temperature of Bangalore on January 15, 2050, I cannot tell you. That's not possible. Okay, that you must understand. That when you predict future, you predict only broad pattern, not specific scenarios and specifically that one. Okay, now the other important I want to mention about these models, you must remember, these models we are running, ocean, atmosphere, chemistry, everything put together, there are at least 50 parameters, 50 numbers you're putting in, which are not known precisely. 50 values are there inside the model, which is not known from first principles. Okay. Now, these 50 values that these models have of the order of 50 parameters. So what this group did in England, Srinivasan et al., and they went to all the experts who run these models and asked them for each parameter what the upper value and lower value, because the parameter is not known precisely. So some number every 50, maybe 60, maybe 40. So you took all those numbers. So for each of these parameters, we had upper value and a lower value and a middle value, 3 values. 3 to 50 are 150 possibilities, right? They ran what 150 times. Okay? And this is distributed here. So the models show that when you double CO2, the temperature typically should be around 3 degrees. But depending on the parameter used, it can be even 12 degrees. So this is a real warning to us that the future temperature is not known precisely. It may be, the mean value is around, the 50% probability, 45% probability is around 3 degrees. It can even be 10 degrees, 8 degrees, 6 degrees. And if this happens, it's a disaster. With the 10 degree warming of the world, I can tell you, the world will not be the way we are seeing it today. So this is something you don't understand, that people think, okay, you said model saying 1 to 3 degrees, but models are not very good, maybe it's not 3. Yeah, maybe it's not 3, it can be 10. The optimist think that it will be 1 degree, but 1 degree chance very low, you can see that. There is almost 0 probability that it will be 0 and 2. 0 probability of no warming, 0. Okay? Probability of 2 degrees very low. 2.1 maybe 5%, 2.5 maybe 20%, 3 50%. So the point is that if you talk to any insurance company and who do risk analysis, okay, they worry about this part, not this part. This is the point you are worried about. Okay? You are gambling on the future of Earth's climate. And if you are a smart guy, you will worry about how to handle this risk. Okay? Now, this is what people, most politicians and bureaucrats don't understand. They will understand if it involves their own health, because somebody told me if I smoke, there is more than 10% chance that I die, I'll stop smoking. Well, I don't stop, but if you are smoking, you will stop smoking. But when it involves the world's climate, we are all ignoring. What you can see clearly is, take this part of the curve, beyond 5 degrees in which the world's climate will drastically change. This number is very hard. This probably, we add all of this, between 25% probability that more than 5 degrees. That is a very serious issue, not something to be looked at, because if it happens, it will be disaster. But remember that models are not good enough to tell us it is only 3 degrees. The chances are very high, 50%. There is a very large chance that it is one of these numbers. Okay, why is that the whole range coming? The whole range is coming because although all the water by carbon dioxide increase, these things are changing water, water control, these feedbacks. They are not saying different models. some models decrease cloud, some increase cloud. Water vapor in all models go up, but they go up in different ways, different amounts. Vertical stretch is different. So the whole range of temperature getting the same perturbation is because of these changes. Okay? And this is something which will not immediately improve. A lot of research is going on, huge amount of money being spent, but remember that still our understanding as you do will take time, not going to have overnight. So the fact of the matter is, we have to live with this uncertainty for the future. But it's important to understand from the point of view of policy that this is a very serious issue, because there's a small probability that temperature will be very, very large. And if you are sane people, we will make sure that will not happen. Now, let me repeat what I said about the past. In the past, I said the sun was the main agent which changed. In the 20th century, 21st century, the main agent is this, which is what we are doing, distributed heat, and that causes about 1 degree change in temperature. That 1 degree causes change in water vapor, which increases, it melts. So these two add along the cloud, along the cloud, these can add another 2 degrees to the dynamic. And 2 degrees in the mean, but some of the model results also can be 9 degrees. And 10 degree increase is due to additional feedbacks reduced by clouds and ice and other things. So this is where we are. So what I want to understand in climate change where we are. We are right now here, 2010, somewhere here. Okay? So you can see why there's so much debate going on. Because this number is not very different from these numbers. The last 1,000 years of data here. So this slightly going above the. There has been slight cooling over the last 1,000 years, and now the slight warming. Okay? So if you are a skeptic, you can say, no, it's not yet. The fact is that the future looks very bad. The future, this direction is way above what we have in the past. And all the discussion and all the arguments that are going to take place in the next 50 years is about this issue. Whether we are here or we are here, we are going to be here, maybe it's okay, we may survive. If we are here, then trouble. This range, which is due to that distributed resolve, is what is the debate is all about. Debate is all about preventing this from happening and hoping that we can confine ourselves somewhere here in the region. Okay? But I wanted to appreciate the fact that we are sitting somewhere here where the message is not so clear. We are fairly close to this and not yet reached anywhere here. So it's a matter of just 20, 30 years, you will see the signal come out very clearly, and all the silly debates going on today among political nations will go away. Now, the only bad news is that you don't know when this will happen and how it will happen. Now, for this, I must give you a background story unrelated to global warming. It is the ozone hole controversy. Now, you must remember that ozone hole is caused by factors very different from global warming. They are totally unrelated, unconnected phenomena. They are connected that both happen because we human beings abuse the environment. That is a common reason. There's no other reason. Now, I was telling you this because when I was a student, this issue came up. The effect of releasing these chlorofluorocarbons on the ozone. And 1972 there was a publication. And people made fun of it, laughed at it, and said, oh, it's not possible. And how can I do this? Because you remember that chlorofluorocarbon were considered as a miracle. They were created in a laboratory. They are non-toxic, non-flammable, non-corrosive. Think of anything, it is safe. It is the safest chemical made by man. Okay? And as an engineer and mechanical engineer by training, we all thought it is the gift of human being in the world. And absolutely, you can put the CFC in the lab, nothing will happen. You not even know it exists. It doesn't smell, doesn't corrode, it doesn't nothing. Such a harmless chemical had a dubious impact on the world. And when the first pointed out, people didn't believe it. And more people published in the 70s and so on, still people didn't believe it. Ultimately, one fine morning in the 80s, some people were making some measurement of the ozone in the Antarctic. Just for fun, not that we are thinking about those days nobody knew what. Suddenly they saw a huge decline in ozone in the Antarctic. And the first reaction was, interestingly, that there's some error in the data. Because nobody expected it to happen. Okay? The first data came, they said the data is wrong, please throw it away, check the instruments. Now, luckily, purely lucky, that at the same time this balloon was being made in Antarctica by the British, the NASA had a satellite to measure ozone and go globe. That also showed a decline. Then they woke up, and these two groups are not together, in different domains. So one fine morning, somebody said, you know, we heard that NASA said also show the ozone decay. Then suddenly they called a meeting, and then they realized that they are seeing a huge decline in ozone, which no model predicted, by the way. All these models which were run at that time, many of my friends were not in it, showed a slow decline in ozone over a few percent over 30, 40 years. Nothing to be worried about. But it happens like this. Okay? So as soon as the report came, people got back, so people argued why models did not predict. Finally they realized that models had a big weakness, which is they did not take into account heterogeneous reactions. All the models my friends were running, my other PhD students are running, were in the same lab with mine. They were running models in which they assumed that there's only gas-phase reaction, homogeneous. They did not realize the role of surfaces, catalysis. So that was not even thought about those days. But once the expert data showed a dip like that, within 3 years people brought beautiful papers showing white after the event. So the message is that the models are showing increasing temperature. It may not happen the way the models predict. It can happen in much worse way also. If the models do not incorporate some physics, which we do not know today, like in the 1970s, we did not know heterogeneous reaction. Maybe something going on in clouds or in something which we or you don't know. It can happen. I must mention a very interesting side story. And how many of you are Narlikar, is a well-known astronomer in India, who writes beautiful science fiction. And how many of you read science fiction areas, right? He had a beautiful paper published 30 years ago in one obscure CSR journal, in which it starts snowing in, I think, Delhi and Bangalore. Okay? And it's a science fiction story. So suddenly Indian scientist finds out that under certain condition, snow can form at a different temperature than other conditions. So it's an interesting story. So what I'm trying to say is that we don't know enough about way ice forms, snow forms, that we cannot rule out that there are situations which can occur in the global climate scenario, which can produce new form of clouds, new kinds of ice particles or snow particles, which are totally different properties than what a model has. That is possible. So what I'm trying to say is that this is what the model predicts, but actual thing they go like this also. That we don't do. So that's what you remember, that the models are not perfect. It can go wrong both ways, in a worse way or a better way. So that is what, and I said, if you are a sensible person, you will allow for errors on both sides, not only one side. So the allow for error also, in a way, much worse than what is happening to me. Okay, so that's how I want to add this feature. This is the feature which is causing a most problem. This we understand well. This we understand reasonably well. This is the one which is causing problem. Okay? So this is the one which is going to continue to cause problem, although the number of research projects has gone up exponentially in this area, but still, I don't think it's going to dramatically change or understand overnight. It will take time. So this is the major cause of all the models will agree on this portion. This portion may differ a lot. Just to give you a flavor of how tough the problem is, I'll tell you how many features cloud has. One is you must know what is the cloud fraction correctly, because clouds are overlapping with each other, so how much they overlap, and how they interact created. We'll talk about that later. You must know correctly that cloud top 5 and cloud base 5 to get everything right. And you have to know the amount of liquid water in the clouds correctly. These are all what called microphysics. That is the big picture. Then you come to hydrophysics. You must know whether ice or water. That's very important. Ice reflects more than water. You must know the size of the particle. Liquid water has a typical size of 10 microns. Ice has such that bigger size. You must get those things correctly to get the reflection correctly. And you have to get the shape right. See, in the case of liquid, it's always spherical, no problem. Surface tension demands that. But in the case of ice, it comes in, and snow comes in variety of shapes. There are hundreds of varieties. They're not got all of light observationally. So that you get, right? You get the again reflection of the concentration. And how are these inside the clouds? This is called microscope. So you get macro line, micro line. And of course, you must know under what environment the cloud is. That is descending, ascending, all the way. So all these factors, which is 3 plus 3, 6, those are 8. We are not qualified so far. We know that. So we compare different models, they differ in these 8 factors. And as I said, this is the area of research. A lot of people in this center are doing research, but they are not going to solve the problem overnight. It is a tough problem. Huge amount of work needs to be done. And so, unfortunately, we can't afford to wait for these models to all get it right. We need to act before models really work the truth. I'll give you an example. Don't look at only these two. These are 2 different models predicting the temperature change of the CO2 doubling. One says 3 degrees, one says 1.5 degrees. 2 different models. Why is that? Because in one model, the cloud goes up, reflects more radiation, and so on. Another model, cloud increases. More clear sky, so temperature goes up. This is the main difference. And we don't know who is right. I cannot tell you this one is one wrong. We don't know because if you look at the present climate, the model prediction of the present cloudiness of the Earth is unfortunately it's varying within the error bar of measurement. Measuring cloud is very tough. One of the toughest thing to measure in the world because it's a highly varying quantity. So our knowledge of the cloud is about amount of cloud is about varying by 1 or 2%. And in that, these are that way, these 2 models. So you can't say who's right. But in the future, you're showing totally different. Okay. So that is the unknown part in the model. Now, I want to also bring another fact because this is important for people to understand climate change. See, we always think about CO2 increase causing warming of the Earth. But you must remember that CO2 increase will also cause cooling of the stratosphere. About 50 kilometers, Earth is going to cool because of CO2 increase. Now, this all we must think about is a very important thing to understand. You must remember that must remember that here is the Earth, here is CO2. Okay. Now, this CO2 traps as radiation, so it won't have that's no problem. This goes up because this traps radiation. But remember that if you're looking at this region of the Earth, the stratosphere, because CO2 has gone up, it can also emit more radiation. Not absorb, only emit more. So it can cool the space much more easily. So the CO2 increase in the last 100 years has warmed the surface of the Earth, but has cooled the region above about 15 kilometers all over the world. Now, this is a very important result, both from the point of understanding science as well as understanding the cause. Because there are people even today, there are people like Prof. former chairman of IISc, who claim that all the change we have seen are due to the sun, not due to me. But he cannot explain this. If sun output increase last 100 years, it may have become wrong. Then the temperature will increase everywhere on the surface to top. Only CO2 increase is a very funny character that it warms the surface of the lower troposphere and cools the stratosphere. This is the fingerprint of CO2. This is what the fingerprint. So, as a matter of fact, the fact that all observations show that temperature has decreased in the stratosphere and increased in the troposphere clearly proves that what happened after 100 years is CO2, not with the sun. So, we do prove. Now, people will still dispute that because you can see, I hope you can see that the error bar is very large. Because remember, there are not many balloons reach stratosphere. Very tough. Balloon can go up to flight quickly, no problem. But after that, the balloon has a problem. So there are only maybe all over the world, a few, maybe 100 launches a day which are measuring stratosphere. So there are problems with data, that's why error body is very small. You see the error body very large. Still, as far as sign is concerned, sign is very important, the number. Notice that this is minus 0.6, this is plus 0.1. Huge difference. Okay? So there's no doubt that stratosphere is cool. Yeah.
Why is CO2 cooling in the stratosphere?
Huh?
Why is CO2 cooling in the stratosphere?
I suggest that the tutorial you have to do a problem. Yeah? It's a very tough question to answer in a simple way. So in the afternoon we'll have a discussion. I'll put up a model. You have to do an angle plan stratosphere and you can show it. You can discuss the problem. The results are not easy. After we have tutorial, first doing the surface and the troposphere, then we have the discussion on the stratosphere as to why it should be. It's not easy to answer. The simple answer is that increase in CO2 in the troposphere allows you to absorb more, it also allows you to emit more. Okay? That is the key point. So, because it absorbs more radiation from the Earth temperature goes up. So, Earth cannot get rid of the heat. But the same CO2 at upper level is able to get rid of the heat. So, that is the point, but this answer is qualitative. You want a quantitative answer, you have to write the equation down and we can discuss in the afternoon. Now, this analysis for this picture, suppose you increase the sun's radiation, okay? Everywhere temperature goes up. If you increase CO2, temperature will increase only in the troposphere, not in the stratosphere. If you increase sulfate aerosol, it will cool the troposphere and warm the stratosphere. This happens during every volcanic eruption. Earth cools, but the stratosphere warms. Okay? So remember that each, only look at this side, each of these processes has a fingerprint. The fingerprint of this is warming everywhere. Fingerprint of CO2 is warming the troposphere, cooling the stratosphere. Fingerprint of sulfate is reverse of this. Okay? So this is a very powerful data that by looking at the vertical changes in the temperature, you can pinpoint who was the culprit. Who is the murderer? It is the sun, human being, CO2, or you can do. That is the beauty of this vertical structure of the atmosphere. And all of them combined is called what we see today. Ozone is a different structure, is a different quantity. Okay, now I want to end this part of the discussion by comparing the temperature changes in the past with the future, that is the 20th century. Now notice that in the last 1,000 years, the amount of methane atmosphere has gone up by a huge amount, coming 800 to some huge amount. CO2 has gone up to almost 400 ppm per day, well above the past, well above the past 400,000 years. But temperatures are not down. Okay? Temperatures remain fairly close to here. So this, again, something which all these skeptics jumped out and said, you see, something is happening, take care of us, we don't know what God is there, help us. This is nonsense. You cannot abuse the earth, God will help you. That don't abuse God. A lot of people, religious students in this world are saying, don't worry, God is there to take care of it. I hope we call that right. Unfortunately, we can't. We are abusing the earth, we have to pay for it, we have to penalty for it. So the reason why this is not changing is clearly very interesting. Why this is not changing, but these have changed dramatically, is for two different reasons. One, earth has a huge inertia. Ocean is sitting there with a huge amount of mass. So it's not going to react immediately to your abuse. It's like a huge big Gunda there. We'll take some beating from you and then come back and hit you. Okay? We'll wait for you to. So this ocean is keeping the temperature change occurring immediately. The atmospheric changes are very rapid. Gas changes are very low time constant. There's huge time constant. So whatever additional heating CO2 has imposed on Earth is not yet seen. It is there in the ocean. It's going to come up in a big way slowly. First. Second thing is more interesting. Second thing is because of the aerosol. See, CO2 increase should have caused this temperature rise. About 2.5 degrees. This is what you described. But actually it is less because of this cooling by sulfate aerosol. So the answer is two things. One, it has not gone up because part of CO2 increase is counterbalanced by sulfate aerosol. Secondly, because of the large inertia of the ocean, the temperature rise is occurring about a couple hundred years later. It will come like this. Then the late, it will land because of inertia of the ocean. Now, the other problem we have in India is that aerosols come in a variety of forms. There are natural aerosols and man-made aerosols. And in India, we are very complicated when you look at monsoon and so on, because, for example, during the winter season in India, there is a huge amount of soup, black carbon. In the month of this month, March, in North India, it's amazingly high and very bad for health. And during monsoon, it's cleaned up, and next year again, it brings up. But during the monsoon, it is not the human aerosol, but natural aerosol coming. This is dust. Okay? So when you're dealing with aerosols, again you're worried about natural versus man-made. And in Indian region, both are interactive, very complicated. Okay? And Professor Satish will talk about this issue in a separate lecture. Okay. Now, when we come to the whole issue of what happened in the last 10 years, so in the last 10 years, temperature has not changed. Okay, compared to the previous 30 years, you can draw various lines to represent these. But the fact of the matter is, it has not changed. And as I pointed out, last 10 years are unique. Both are about the way ocean is behaving and the way sun is behaving. So it's not surprising this will happen because Earth system is not a linear system that you put in additional heat trapping linear temperature rise won't rise. There's a lag phenomenon. There is a question of ocean response time, and so all those will play a role. Later it will come back up. But still, this has caused a lot of controversy only because many models are not able to capture this part. This part where the ocean is not changing, models are not doing too well. So we know that these models are not good at handling what are called decaying rate. Decaying is 10 years scale. You're not good at that. You still have to learn how to get those parts right. So we are admitting that we are okay on a long time scale. We are not okay on a short time scale. We don't know what's happening. So this is a deep point of the problem. And a lot of newspapers who are run by industry who want to attack it, they are pointing out this from Daily Mail in London, saying that models have predicted this change. And what's happening with this? So they are saying, you see, models are all wrong. Now, this is a very simplistic view. We know that these models are only good to predict changes over 30, 40, 50 time scale. They're not good over 20 time scale because other things going on in 20 time scale. So you cannot expect that models will get every little thing back. It can't. It doesn't have that kind of physics in it. But yes, you have to admit that there's a flaw in the model and what is going on to see why this feature of the last 10 years was not fundamental. And one of the reasons, of course, I told you was that all the additional heat that CO2 has trapped on Earth is in the ocean. 90% is in the ocean. Okay? Little bit is in the land, little bit in the atmosphere, but most of it is trapped in the ocean. So this is the thing which will ultimately have to come out as the ocean surface changes. Okay? So that's what is delaying the heating of the atmosphere. Now let's look at rainfall because although I have global warming temperature, global warming temperature because that's quantity which can be accurately modeled. Most people who live on Earth are not living on a global warming scale. We are all living in Bangalore and Delhi or Mumbai. We want local observation. Unfortunately, wants a rainfall. One example is the work you are doing in the center on monsoon rainfall. I'm just comparing the observed seasonal cycle only with various models. Okay? And you can see a huge variation. Only 2 or 3 models get the peak right, and very few models get the season setting right. So this means that if these models are not even able to get the seasonal cycle of rainfall correctly, I cannot trust these models to predict future rainfall. So all these, those people, one of you said we are going to look at future hydrology, God help you. The models are no good. Okay? Those of you who are doing hydrology of the future are living in an imaginary plane, not real plane. Okay? Because no model can give you rainfall over India accurately, unfortunately. And this is the truth. Sometimes people are hesitant to tell this in Delhi because they won't get funding. But I don't mind telling people in Delhi, sorry, don't expect us to do miracles. This is a tough problem to solve. Nobody in the world has solved it, not that we are not good. Nobody in the world has solved the problem correctly. Because there are a number of issues about clouds which we are not understood at all. That's why there's a huge rain. Imagine one cloud can get the rainfall of 2 millimeters per day over India. The observation is 6. So these are, most models are not bad, but even this is bad. If your model is getting 4 millimeters per day over India, that's a drought. Most of us won't survive. Have a 4 millimeters per day average for 100 years, won't survive. Okay? So you have to accept the fact that almost all the models are having difficulty in getting rainfall correctly on a regional scale, globally too. So that if somebody is asking you to predict impact of climate change on rainfall, the answer is you can't predict. And unfortunately, in India, a large number of NGOs and people are promising government that they will tell them what happened in the future. It wasn't an astrologer to do that. Okay? Can't do it. And just to give an example, if you look at the mean rainfall and its variation from year to year, that is observation right here. And no models can handle that. Some models are not bad, but many models have either too low rainfall and too low variability, or too high variability, and all kinds of things are going on. So until this is fixed, we can use this model to predict future rainfall. So I generally do not look seriously at the rainfall prediction on a regional scale because they are not very good. But temperature is different. I want you to remember this important message that temperature prediction is very accurate, rainfall prediction is very poor. But unfortunately, in a country like India, rainfall is more important than temperature. So that's affects our livelihood, unfortunately. But we have to honest answer that we don't know. Here is an example of future rainfall change over India, but their same models is a huge range. About half the models say rainfall go up, or half the rainfall go down. Another says it's almost, it is a 4 millimeters per day. So you can, so the net story is we don't know. If half the models say rainfall is low, half say rainfall is high, the main answer is we don't know what to find. Okay, another important issue about global climate change, what which I don't have time to talk about, maybe others or others, is sea level rise. Because although I can't tell you what will rainfall in the future, I can tell you sea level will go up 100%. Because that is purely simple physics. As temperature goes up, sea has to expand. No problem. Ice has to melt, and expand more. So both are guaranteed. The reason why you are worried about the following, this shows and in graph. Overall, gradually, not much, about 1.8 million. It is not a large amount. But see how it's changing. First 30 years, next 30 years, the last 30 years. So it's exponentially increasing. Okay? So now it's a lot of 4 million per year right now, from satellite data. It will go up to 5, 6, 7, 8 and the global one. So this is the thing which worries because, again, remember that all the heat is stored in the ocean. And the ocean is warming, there's nothing to do with it. And when it warms, it will expand. Expanding, it will increase sea level rise. And so this is the most important impact of global warming which we can predict without any doubt. Rainfall, we don't know, but definitely sea level rise will go down. And the reason why we are worried about it is that large number of cities in Asian region are right on the coastline. I think we have at least 25 cities in this region which are million more, and all of them are going to be exposed to the rise. That's all. Okay, I'll stop here because I have time limitation. So, if any of you want to learn more about this, in Divecha Center we are very keen on outreach. So many of the lectures given by our invited professors from abroad, they're all there on the website. We also have a YouTube channel, so you can watch more information about climate change from these sources. Okay. Yeah, so what I learned is now that this is where we are going, and if you are sensible, ultimately we will go this way. And this change from this to this will occur if today we take a decision. If we don't take a decision today, we will not. So we are in a very important decade, this 2020 decade, that if our political leaders all over the world are not able to make up their mind, then all of us are condemned to go along that route. And it shouldn't bother me, I won't be around, it should bother all of you. Okay? So that's what I mean. All the young people are worried about the fact that the leadership in the world is in my age group or even older than me. And they don't care. You can understand. When you are at that age, so that tradition now, the world is getting back. I'm not wrong. But it will affect you people. So I think it is important that the young people in the world have to realize that the true negative consequences of global warming will face by done not by leaders who are all over the world, who are all over 60, who don't seem to be worried about what's happening. Okay? So I think I'll stop here because I'm running out of time. Yeah, this is one somebody asked, so I put this slide here. So this is the interesting recent result in published Nature, which shows that 18,000 years ago, Antarctica warmed first due to the sun geometry, the sun curve. And after Antarctica warming, immediately carbon dioxide is blue here increased. It came out of the ocean. Once carbon dioxide increased, the global temperature after about a gap of 1,000 years increased. So this is the true proof that the warming from the last ice age, 20,000 years to today, was mediated by CO2. First, Antarctica warmed due to the sun radiating more there, and that caused the CO2 to increase, and that CO2 increase caused about 1,000 years later to change the ocean temperature. And so this is the sequence of Antarctica and CO2. So this is very nice. It is available in last in Nature. And those of you can access it, I'll tell you, it's very nice paper to read. The paper is just 5 pages long. Okay? Just 5 pages long. But it's going to read. But I wanted to read what they call supplement. Supplement is 50 pages. You know what? Because when they submitted this paper, the referees asked very tough questions. Okay? You have to answer all of them. So they took 50 pages to answer the question. Please read that. That shows how science works. Many people here don't understand how science works. Science works through criticism. Many people here in India are afraid of criticism. And somebody criticizes them, people get very upset. Remember that only way science will be criticism. So please look at this paper as an example of how science is done. This is I think this paper has about 10 authors, it's a big group. And they took data from 80 different cores in the world, combined them very carefully, and they made many assumptions, many approximations. Each one was challenged. So there are about 50 questions, and there are 50 pages of answers. And you read it to understand how science is done, how careful people are in looking at data, how they put it together, and how much of effort and thinking is required to get a result like this. One figure like this involves 5 years of work. You cannot see it, it's a nice figure, but 50 years of 5 years of effort is on it, and 80 different cores are used. That means maybe 1,000 people worked on it, because different groups are there. So this is a beautiful example of papers. When you understand, I think I will copy it, you can read it. So this first paper demonstrates clearly that past climate changes occurred because the temperature went up first, and that increased CO2, and that ultimately led to. Okay, I think I'll stop here. Other things in this presentation, but they're all to the second. Now let me go to the next presentation, which is relevant to what we'll do in the afternoon. Yeah, so this part of the lecture is now about simple climate models to understand what's happening. Okay? And I'm very particular about this because to me, all this year so far are results from complex climate models, and we don't know what the models contain. I'm telling you, you believe me. We don't know, I may be lying, I may be telling untrue, right? So finally, you want to really understand something, you must be able to do calculation with your own hand. Computer is fine, computer is a wonderful tool, does very great things, but your true understanding of the problem comes in when you can pick up pencil and paper and hand calculate the change. You can't do that in the real world, you have to do simple models. Simple models are gross approximates to the real world. And their aim is not to get correct quantitative result. Their aim is to give you insight as to what is happening. Okay? So in that spirit, these are sometimes called toy models. They are toys you play with to understand how the real world is like. And so I want to illustrate that, and often I will give problems to do it actually, so that you have a real understanding of why Untitled is working and how is it working. Now, basics you need for that only two. One, a little about black body radiation. All of you have heard about it somewhere in your high school or college. So this is the intensive black body radiation as a function of wavelength. And the important message of this figure is that at high temperature, the sun's temperature is here. Sun is around 600 degrees Kelvin, 5000 degrees Kelvin. The peak emission is around 0.1 micron. Okay, this is 1 micron, 0.1 micron. On the other hand, Earth is emitting temperature around 288 somewhere here. So the peak emission is around 10 micron. So that's the key difference in the spectral nature of radiation between Sun and Earth. And that is what really controls the Earth's climate. So that you have to understand from basic black body radiation physics. Okay? You might ask me, is Sun really a black body? Is Earth really a black body? Answer is no. Black body is an approximation. Black body is an idealization which some great genius like Planck conceived. There are very few real world objects in black bodies. But still very convenient to understand what's going on. Okay? So let me give an example. This is the radiation of the sun, the black. The black line here is radiation measured by satellite outside the Earth's atmosphere as a function of wavelength and the intensity, okay, of radiation. The dotted line is the function plotted based on black body emission period. Okay? Now, you can say that sun is not a perfect black body, it is not, because there are places where it is emitting more. But you can clearly see that a black body radiation curve from theory comes very close to the sun overall. Okay? It goes very close to it, not exactly. At the Earth's surface, it is very different, of course. At surface, then we have the black body because not so much than top of my. But if I get to that, we look at this outside the Earth. Now, outside the Earth, radiation of the sun is very close to black body at 500 degrees Kelvin. We'll utilize that idea in our problems. Okay. Now, we know that sun radius approximately 700 million kilometers. That's measured by the solar disk. And we know that the distance between the Earth and the sun is 150 million kilometers, also we know. And based on this, we can calculate what is the radiation coming outside of the surface. Very easy. This is a simple thing, all of you should know that. The sun is here emitting radiation in our dimension. And Earth is somewhere here in orbit around the sun. Okay? So whatever radiation the sun emits, it has across the imaginary sphere of the Earth's orbit. Okay? We assume it is right now not an ellipse but a sphere. And so whatever radiation crosses here must cross here. So whatever it is the sun's radiation, multiplied by the sun's radius, sphere radius, has to be equal to what is coming here at the Earth's orbit. I'll call it solar constant, times this area. This area is sphere of the Earth sun distance. All of you see that simple energy balance, that whatever radiation leaving the sun has to cross an imaginary sphere which is the Earth's orbit on the sun, right? That's all that. So the flux you will receive on the Earth outside the atmosphere will be equal to whatever is left here, which is this into that, and the flux will be this into that, so we get this value. This value is not calculated. As remarked, this is the black body radiation, you know, it's 10 to the power 4. That 4 will cancel out. 4 cancel out. So you are getting this result, and when you put this number, you get a number around 36. This number is low. The correct number measured by the satellite is 136.5. This is what I'm going to use in my discussion. This value is slightly outdated. So we know exactly how much radiation coming outside the Earth's atmosphere, and that data now is very accurate because over the last 50 years, satellites have measured it very accurately. Of course, the 11-year cycle, slight cycle is there, but that we ignore right now, the 11-year cycle. Okay, now the first thing we do is we ask that if the radiation from the sun, we know how much is coming outside the Earth's atmosphere. And we know that a certain fraction is reflected by the cloud and the Earth's surface and so on. And the fraction reflected is called albedo by definition. So, S is the radiation coming in of the atmosphere, and the fraction reflected is this into alpha. Okay? And what is coming in is this. So this is what is absorbed. Okay? This is radiation is absorbed with the Earth. Okay? But there's slight complication. The Earth is rotating. Okay? And radiation coming from the Earth, from the sun, is not coming normal to the Earth's surface, it's coming at all angles, right? Because the Earth like this, it's coming at all angles. In the polar region, hardly it's seen, it may go through. So, what is relevant as far as the sun is concerned is not the surface area of the Earth, but a cross-sectional area. Not 4 pi r square, pi r square. Okay? So, what actually is intercepted is only this much. Clear, all of you? So, so much radiation coming in, so much is reflected. So, what is absorbed is this and this. And it is absorbed only over area, the cross-sectional area of the surface. On the other hand, the radiation that the Earth emits from all the surface. It emits equally in all directions. Everywhere. Okay? So total emission from the Earth, okay, is equal to emission per unit area, this is called overall into 4 pi r square. This is called, this is the emission per unit area on surface called Alpine boundary radiation. Okay, so this we'll talk about a bit more what this is all about. Now, in this slide, that we talk about, we're not again let me see that. So, the point about river is that two things. One, the radius of the Earth is irrelevant, it cancels out. It plays no role in your calculation. Then, whatever the radius, those things cancel out, pi cancels out. So the simplest equation which I am going to use repeatedly in this discussion all it says very simple, nothing very great. The absorbed solar radiation has to be equal to the emitted boundary radiation, that's all. Very simple balance. Okay? And this 4 is coming in only because the surface area of the Earth is 4 times the constant. That's all, and no other reason. Okay? So if you want to calculate everything per unit surface area of the Earth, then you divide the solar constant by 4. Okay? So we will do that. The 1365, the number we call S, we divide by 4. That's the number we are going to do. That is equal to 341.25. That's the number we are going to use mostly. And radiation coming into Earth per unit surface area of the Earth. Okay? Everything calculated per unit surface of the Earth, and that is the number. Now, why is this result so interesting and so important? Is because this is known precisely from satellite measurement. This is also known precisely from satellite measurement. This can also all the 3 quantities vertical satellites. Okay? And all the three quantities are very well known, not only for Earth, but every planet in the solar system. For Mars, for Venus, for Mercury, Jupiter, all of them we know these numbers. Very well known. Okay? All of them satisfy this equation. So this is the equation of which you have no doubt. Okay? You can measure all the quantities and they are in balance. So that is one thing to remember. This is a very understood picture. Now I'll cover this later. So this is the example here. You go to Mercury, the solar constant mass of Mercury goes to Earth, with very high solar constant. Earth is around 341, 342. Mars is lower, because Mars is far away. Venus is higher. So this is the solar constant for all these planets, depending on the distance. And the albedo, Mercury has no atmosphere almost, so it's absorbing most radiation. Venus has a very cloudy atmosphere, you can't see the Venus surface, very high albedo. Earth is in between, and Mars is lower. And based on that, you can calculate, suppose this OLR, you don't like to go to OLR, you make it equal to sigma effective temperature of the planet. Right, this way you can calculate this quantity. So not real temperature, effective temperature, and that quantity is going here. It is 225 K over Earth. Actual temperature surface is 288, not 255. So you have now got a little bit more to understand what is this temperature is. And the worst is Venus. Venus, every temperature is lower than Earth because of the high albedo. But actual temperature of the surface is 500 degrees Celsius. Something is going on there under some molecule. So this equation is absolutely no problem there. Absorbed is limited, it's satisfied. But this is not very useful to you. Because I want to know the surface temperature, not the effective temperature. Effective temperature is a concept. There is no value, it is convenient, but it has no value. Now to understand surface temperature, this balance won't help. This balance does not explicitly model the atmosphere. Atmosphere is not even discussed. We are treating the Earth atmosphere as one which is a combined system, we are not trying to separate it out. So we want to know surface temperature, it is more worth. Now, before that, I will also point out that this quantity called albedo, which is the reflection of the solar radiation, it's a very complicated quantity. Why? Because the radiation of the sun is not reflected like this imaging reflection. This very light reflection is very rare. Maybe ocean, when it's very calm, it will like this. Most of the time, reflection is like this, very complicated. Depending on how rough the surface is and what kind of properties are there. So the biggest challenge of the space in calculating albedo of the Earth was to have models for how ocean, land, trees, clouds reflect radiation. Very complicated model required. And you will not believe it, over the last 30 years, the major space agencies, especially NASA and IISc, must have spent close to, I would say, 1,000 crores for this, on this project. 1,000 crores is spent. The calculate is coming. It's that tough. It's a very difficult quantity. You have to look at every region of the Earth at different times of the day, at different angles to know what is the reflection, and averaging all those angles. I'm skipping all the detail, giving a number. I think you must remember that the reflectivity of the surface depends on wavelength. I'm just giving a few samples, we'll know more about it from what I think when it talks about glaciers. Look at wet snow. Wet snow is highly reflective in the visible, 90%. The same snow in the infrared is almost completely absorbed. So you have to account for all the differences with wavelength. Okay? And look at soil. Soil is highly absorbing in the visual, but not so absorbing in the infrared. So all these complicated, like graphs, look at it. The reflection is high in the green region and it comes down. So all these are accounted for. The wavelength dependence, the angle dependence. It's a very complicated thing. So it is, we covered over 10 lectures in our course. I told you in 10 minutes or 10 seconds. Okay. So you take an OR and already effective temperature is 255 with that. There's no BG, there's some number, it is not related to surface temperature. Now, we all know that I'll repeat this. What is missing in this? Similar order, but is not explicitly modeled here. You have to model it, and you have to account for the fact that the Earth's atmosphere is transparent to solar radiation almost, no absorption, and very large across the area. That's what you are doing. Now here is an example from satellite of how the outgoing radiation varies with one. Now you will be surprised, the highest emission occurs in summer. That's because summer northern hemisphere is where the Earth is the warmest. So a lot of land is northern hemisphere, so it emits a lot of radiation, and you get about 240 watts per meter square. On the other hand, you look at the reflective albedo as a function of month. The lowest value occurs in August when all the snow has melted in summer in the northern hemisphere. You have the lowest reflectivity, and then as the winter comes, it starts going down. So in the winter, the highest. That's the radiation. So these are all thought of satellites measured over many years. This is the 5-year average, and this is the best picture we have of the global mean condition. This we already see, and just show the for concept. And this is a quick picture about the three planets which are similar to Earth. Earth reflects about 30%, Venus reflects much more, although it gets more radiation from Venus, closer to the sun. Mars gets much less radiation from far away, and also reflects less, mostly absorbs. And the temperature is very different, surface temperature. This is around 100 we don't understand what is causing the difference. And you can look at all other planets you want. Entire 8 planets, you look at the effective temperature, the distance from the sun, and then albedo. Okay, now to understand what's going on Earth, you need a detailed analysis. That is shown here. All the 100 units coming in, 33, 41, 42, that number. About 3% is scattered by molecules. 19% is scattered back to space by clouds, and 9% by the ground. On this side, so this 19, 9, 20, 30. About 70% absorbed by dust molecules, only 3% by clouds. Cloud is able to reflect, not absorb. So 20% absorbed in the atmosphere. Coming to clear atmosphere, they get clouds. And the remaining comes to Earth. Earth only gets half radiated from the sun. Half goes away to reflection absorption by the atmosphere. Rough number you have to. That is on the solar radiation side. Now you come to the other side, the Earth's radiation. Earth's radiation is very interesting. Of the 100 units coming in from the sun, Earth emits 140 units more. And most of it is absorbed in the atmosphere and is radiated back. That is the power of CO2 and water vapor. The CO2 water clouds the atmosphere essentially trap Earth's radiation and put it back, and that's what causes the warming. There is some contribution, of course, from late 18th century, that is water evaporating from the ocean and so on. But major role is radiation, major. Now this another picture showing how the sun rays coming in and how it into the Earth, and how the radiation from the Earth, most of it comes back, and only small portion reaches the space. Now there are other graphics showing it in different ways. All these numbers are similar. I'll just give you different examples. One more example of the number I call it. Okay. Now I want to get at this graph, get at the equation as what are the absorbed radiations. And this is the emission by a black body. But because of greenhouse effect and other things, emission from the Earth is not black body. So I put a factor as the left is not emission is some other factor. Now, if you ask me, this number is known, 0.3. This number is known, that is 65. And this is the Stefan Bertram Cosmological number. This is known from Planck radiation law. Now, given that we know the 728, given that, I calculate this. This is not a great thing, just back after it. I get 0.622. Okay. A lot of books put this number and say we have given an not given an answer, we only are saying what f should be for it to be equated. You're not proving anything. Now, why is f not equal to 1? Very simple. F not equal to 1 because there is atmosphere between the oceans. For example, if you treat the entire Earth as ocean, forget about land right now, ocean is almost a perfect black body. No problem. It emits like a black body. So emissivity is 1 of the ocean. But whatever it emits doesn't reach the outside space because of the atmosphere. So here you have Earth's surface emitting at 288, sigma raised to the power of 4 will be 390 watts per meter square. That is measured, we know it's correct. Very close to it. Now, unfortunately, what the satellite measures at the top of the atmosphere is around 230 or 240 if you want to be top. So, if you take it as 240, 150 watts per meter square is gobbled up by the atmosphere. Because the atmosphere is there, Earth is not able to get rid of all its heat. It won't get rid of 390 watts per meter square, but atmosphere, no, you can't, you only can get rid of 239. So this difference between the Earth's surface emission and what can go out of the Earth, this one is this. So we get 240 convenient right now, just for round number. 150 watt per square greenhouse effect. And this is achieved by carbon dioxide, water vapor, ozone, methane, and clouds. All these layers, all of them put together, are preventing Earth from emitting 390 and 224. That I must model. Not a model that not open submission. Because there is not there. This kind of calculation is key. You put some number and say I want the right answer. You know, so you have to actually have a model which captures that result. Yeah, this you already seen. I don't want to repeat. All I want to repeat the difference between the radiation from the Earth and the radiation from the Sun. They're well separated and the atmosphere behaves very differently in between. There are hardly enough friendship, lots of matter observing. Yeah, same number is given here. The current varies with, we have got the different that constant. Another way of putting this number, 390 is coming to the surface, so what is going on 150, and 50 is coming back from the, and this is the non-radiative process like radiating. This is the solar side, this is the Earth side. And as pointed out, the repeat is very important that most of the radiation that are not CO2 but by water. That's always forgotten by many people because it's not mentioned in IISc report so on, but that is an important role. Now let me give you an example just to illustrate. Today, if we suddenly remove all the CO2 in the atmosphere, present value is close to 1 ppm, all of it, you will not feel a difference. But within a matter of maybe a couple of hundred years, the entire Earth will be completely ice cold. Why is that? Because you put CO2, the remote is the greenhouse effect. Okay? So the Earth will start cooling. As soon as the Earth cools, all the water vapor will disappear immediately. All of you know from thermodynamics that the amount of water vapor in the atmosphere is exponentially different temperature. Depends on temperature, exponentially on we plot water vapor content in the atmosphere. With temperature goes like this. Okay? So when you remove CO2 and the temperature comes down, then the water vapor will come down and this will take over. Okay? So interesting point is that water vapor is not a free actor in this game. You remove CO2, water also goes down. You get ice age immediately. So who caused ice age? Water vapor. But I didn't remove water vapor. I removed only CO2. So see the important complicated, a lot of people don't understand that the CO2 is an agent. He influences the Earth's climate through water vapor. Water vapor is a dominant player, but he has no, we have no control over the content in the atmosphere. So similarly, when the CO2 goes up by a few percent, it immediately causes chain reaction, this increasing, and immediately increases global warming. So it works both ways, very effective. Okay, now I want to show this up again. I want to illustrate this. I'll take an example from one of my students' work. You take 300K, that's okay, it's not to, I took the topics 300K, limit about 459 watts per meter square at the Earth's surface. And if you had only minor gases like chlorofluorocarbon and something, then you will find that same radiation will almost go through the top of the atmosphere. Little bit less, maybe a few watts per square. Then you add CO2. Add CO2, dramatically the radiation increases. It traps radiation. Then you add methane, little bit change. Then you add ozone, little bit change. Then you add water vapor, change. So how we see how each gas playing a role. And the two important gases are water vapor and carbon dioxide. And others are very minor. Methane, chlorofluorocarbon, ozone, they are all major players. Two major players are CO2 and water. I think I now come to. I'll skip all this and various examples. Now, what we want to do is develop a model of retinose effect. Only on 2 level model, which is what we discussed in the afternoon. This is Earth's surface. I treat the whole atmosphere as one layer, which is completely wrong, but you have to start somewhere, so we'll start with that. Okay? So treat the entire atmosphere one layer, which is a big approximation. But we have to start somewhere. And that atmosphere we assume emits equally in both directions, which is not true, but we'll assume that. And so let's model this. And this is discussed in one of the books, and it's all the one in the slide here. So you do this model and you skip down. This is model analysis. So that layer there is the atmosphere and quantum temperature, T8. Okay? And it emits in both directions, epsilon sigma equal to that's a visible atmosphere. It absorbs a number of solar radiation from about 20%. It reflects radiation that comes below. Remaining comes here. This is all we discussed. So it emits in both directions and transmits a little bit of radiation to space. And so the thing you have to look at is the balance we are doing at the surface of the Earth and at the top of the atmosphere. Two balances are being done because remember there are two equations and two unknowns here. The two unknowns are surface temperature or cross temperature. Two unknowns are there because there's two layer model. And I need two equations. So I balance at the Earth's surface. The radiation coming in. The radiation emitted by the atmosphere downwards. To the surface. All the three have to be in balance. This is at the top of the atmosphere. The top of the atmosphere, this is the radiation absorbed from the sun. This is what is lost from the atmosphere. This is what is transferred through the atmosphere to the surface. So these two balances put together get this result. This result I'm going to discuss in the afternoon in some depth. Because this result brings out very clearly how the surface of the Earth depends on the Q's aspect force. Q is nothing but aspect force. I'm not written that. It's written there. It's important. That number 3.2 point. Okay, that's all I'm talking about. Now, what it shows clearly how is temperature of the Earth's surface depends upon the incoming radiation, depends on the reflected radiation from the Earth or below. Depends on how much radiation absorbed from the sun by the atmosphere and how much the atmosphere will emit. So 1, 2, 3, there are 4 parameters in this one. Very simple example. And you put some decimal numbers, we'll get one of the problems afternoon. Now numbers we're going to use in afternoon are, we'll assume the albedo to be around 0.3, which is close to observation. We'll assume solar observability around 0.8 close to observation. Solar constant we're going to use is at about 1.25. Okay? And we find out that we assume the emissivity of the Earth is 0.95, which is not precisely 0.95, we'll get a compare this to 280. So what we are able to manage with a simple model is to get the surface of the Earth close to the Earth by using the satellite measured value of Q and FFO. Satellite measured values of R, below. Satellite measured values of A bar. But this is not wrong. This we are actually doing. You know it's right. You know the exact value. it's not easy to that way. This, you get guess down, if you guess to 0.95, you get the answer, which is come here. Okay? It's not a perfect model, there are better models, but this model is good enough for us to discuss. Why is this model so useful? It's not useful because now I can ask the following question. Suppose we added carbon dioxide to the atmosphere, more carbon dioxide. How will temperature change? Now, when you add carbon dioxide, it won't change this, it won't change this. Beginning. Okay. It only changes. So I can ask the question, how does the surface temperature of the Earth change in response to change in visibility? Okay. All of you can calculate, we'll do that in the afternoon. You can calculate for 1% change in visibility, what is the temperature change? Similarly, suppose there's a huge volcanic eruption occurring. And or even more recent issue. Suppose you bring a lot of soot in the atmosphere by diesel burning trucks or in cooking. This will go up. Can I ask this question? How will the temperature change in response to change in absorption to solar radiation? Okay. Can I answer this? Third question is, how does this depend on solar constant? Solar constant changes by about 0.1% for a 11-year cycle. How much effect does it have? That also important. So all these are numbers which will get a reasonable idea of the role of all these quantities in the context of simple model. Now this model is not perfect, I'll tell you that, because this model assumes all the processes going on are only radiating, which is not true. In the real world, the ocean loses heat by evaporation. It is not that anymore. So we are paying a bit penalty there, but still it's okay for understanding the role of atmosphere also. Yes. I calculated this particular actually. I've done this calculation here, but I want you to do all this and check how much change occurs in each of these changes. Okay. Now, if you understand this model better, then you can go to higher level model. You can have a 3-layer model. You can have 2-layer constant concentration. This is troposphere, this is stratosphere. Somebody asked the stratosphere, this is a model you can use. Higher level model. Okay? So, but we need more parameters to put around there. Now, from observation, we know what happens in stratosphere coming around the troposphere. There are different behavior. That's not much like the troposphere. You can use some of these models to understand stratosphere. So, these are the equations. We have a 2-layer model. And then you can plot what the method thinking like this height. This is actually the 2 layers of atmosphere. And this is the surface temperature, this is what the model gives. And so you can, what I'm trying to tell you is, we start with 1 layer of atmosphere, you're not having to be 2 layers. You're not having to be 3 layers, today you can go and add it, no problem. So this is 1 layer, you can add 4 layers. Each layer you do energy balance. You can add n layers. People are done, no problem. Okay. If you do that, you will get the entire distribution that you get in real atmosphere. Okay. This is called the radiative profile. Profile, I think only radiation is the only process. You can, given all the layers here, maybe 100 layers or so, you can calculate how much it varies. And this is the ozone is reading this layer. Otherwise, you not like that. Ozone is called somebody changing the. All that can be done by building on this. So I want to end up pointing out that if you do such a model and you don't have ozone, then you go like this. Temperature will keep dropping with high. And this is water vapor and carbon dioxide. As soon as you add ozone, the temperature profile changes. So the ozone absorbs radiation in the ultraviolet, in the upper, in the stratosphere. And if you don't put that, you will not get the shade is observed. And these are various observations and various calculations. And what you have to know is that in the real atmosphere of Earth, what's happening is the major heating is occurring near the Earth's surface due to absorption solar radiation by water vapor, okay, mainly. And the main cooling is going on in the long wave due to cooling by carbon dioxide, water vapor, ozone, all are cooled. And if you look at the net, that is a combination of solar and ground rate. And net is this ground, and this ground is getting better job. Net is this one. Net is this one, okay? So what I want to realize is the atmosphere as a whole in the net is cooling. That is, the solar absorption is very deep, the long wave cooling is very strong, the atmosphere. So it's cooling in the net. So if the atmosphere temperature has remained constant, the only way it can remain constant is because heat is transferred to the atmosphere by evaporation. If that is not there, atmosphere cannot be equilibrium. So atmosphere is really always cooling. The solar rate absorption is very deep in the atmosphere, always cooling, and this cooling is stopped by transfer radiation from the surface to the atmosphere by vapor, which condenses in the atmosphere and overcomes this cooling. That is one more thing to that. And this should be drawn as well here, the black line is net cooling. And so other people will discuss this part in the lecture. Now finally, let's look at what IPCC talks about. So IPCC is concerned mainly with human impact on climate. So what IPCC is saying is that major amount of heating in the last, since the pre-industrial era, 1950, and last 155 years here. Sorry, this is 255 years. Okay. 255 years, mostly it's due to second methane, third everybody is ozone in the stratosphere. Then there are all these surface effects, all the other aerosol particles. There is some effect of black carbon and snow, which will be covered by the cutting. And there is cooling due to all the sulfate aerosols here. And there is some small change due to change in heating, but it's very, very small. Total is mostly carbon dioxide. So although there are many things going on Earth, but zero thought, that is not that. Remaining the passing on. So that is major, that's why the major focus of IPCC discussion is only on CO2. The rest are not there, not that important. And the trouble is, I want you to realize that we human beings, because of our ingenuity, are creating all kinds of new molecules. And our bad luck is all these molecules we are creating, all of them like this, all of them absorb radiation is the reason why 7 to 50 microns. All these chemicals released in the atmosphere for human beings happen to cause warming. All of them. Such as why it happened, accident there, all the chlorofluorocarbons, they're all here. Every one of them, and the worst part is, these are all in parts of billion mostly. Yeah? So people thought it's not important. It's important because they are observing right where the peak of the radiation emission will occur. Peak of So they happen to have their absorption band right where the Earth is the most effective in radiating out. So they are very effective, although they are in parts per billion. So you must remember that in radiation, what is important is not your concentration. What's important where you are in the radiation spectrum. If you are in the right place, you are more effective. If you are a businessman, you have to be an MG road in Bangalore. You are in this business. Okay? That same way, in case of radiation, you are most effective absorber if you are in the right place in the spectra where the emission is maximum. If you want to absorb Earth radiation, you must be located close to the space. And ironically, whatever there is no band here, whatever is transparent is radiation. It is ozone, methane, all those guys are methane somewhere here. So all these guys, minor players, are getting very important all because they are located, they are absorbing band close to the peak of the emission of the Earth. So that is the unique, unusual part of the Earth. So I will not talk about this interesting issue. A lot of people are now concerned about Venus temperature being 7 degrees Kelvin, because Venus greenhouse effect is about 1,000 times larger than Earth. Huge. Now you should understand why. Because Venus and Earth are twins. They are almost same size. They are born at the same time when the solar system was born. So Venus went one way and Earth went another way. Now, about 50 years ago, the idea was very simple. They thought Venus went that way closer to the sun, it was hotter. That's not true. Venus is covered with clouds. Sun could not do much to Venus. In spite of being crowded clouds, it went crowded physically. Because in Venus, the amount of carbon dioxide is about 1,000,000 times larger than Earth. Okay? But the irony is that the total amount of carbon dioxide on Venus and Earth is same. The difference is all the carbon dioxide on Earth is present as calcium carbonate in the ocean and in the rocks. In Venus, all that has come out into the atmosphere. That's all different. They have the same beginning. Both have no atmosphere to begin with. Both Venus and Earth. All the carbon dioxide was stored in the rocks. In the Earth, it has remained in the rocks, fortunately, and in the ocean. Not in the Venus, it came out. So it's a very good story about Venus, how it built up. And unfortunately, we're not ready to discuss that, but you can understand the references. So the unique part is, you draw the temperature pressure diagram of the different planets. Earth is very unique because Earth happens to be close to the triple point of ice. This point. So Earth is the only planet we know of so far in which the ice, whatever exists in three forms: gas, liquid, and solid. No other planet has that feature. And because it exists in three different phases, it is able to control the Earth's albedo through clouds and through ice, and control the Earth's temperature, which Venus could not do. Venus went way out of that 1 degree centigrade because Venus was only water vapor. There's no liquid water, there's no ice, but it is so large. And in the case of Mars, Venus, Pluto, they all only ice, no water vapor or liquid water. Only Earth, the close to the point of ice, is a unique system. And we need to understand this better. We don't want to go there. And that lunch has come. So we'll be after lunch for more questions and problem solving. Okay, thank you.